Okay, so in this video, I want to talk about normal distribution of data. You may hear that as normally distributed. We'll talk about the bell-shaped curve, skewness, kurtosis, all sorts of things. Now, to get started, I want to make sure that we cover what is normal distribution. There's a bell-shaped curve, that's a graph of normally distributed data. It's a symmetric bell shape. You've probably seen this before. The center of that bell shape is the average or the mean of the data. In a normal distribution, the mean, median, and mode are all equal and located at the center of the distribution. With symmetry, the distribution is symmetric about the mean. This means that the left side of the mean is a mirror image of the right side. So that's how we get the bell shape, where you have the peak and then the right and left side are basically the same. The spread of the data is the width of the distribution. So sometimes we have a very tall peak and sometimes we have a smaller peak, but we have a wider spread out between the right and left. That is determined by the standard deviation. A smaller standard deviation results in a steeper curve, while a larger standard deviation results in a flatter and wider curve. So here's an example of a bell-shaped curve. This is also the empirical rule. Approximately 68% of the data falls within one standard deviation of the mean. Now, this is the empirical rule. Not every single data set will have this, but to have a perfect bell shape, what we're looking at is about 68% of your data will fall within that 1% of the average of your data or the mean. About 95% falls within 2 standard deviations, or nearly 99.7% falls within 3 standard deviations. Again, that mean is your average. The standard deviation is the average distribution of data relative to the mean. So it's the variability of your data. To get this bell-shaped curve or to get a normal distribution, to get this image, we can use a histogram in Excel. We can also do that in other systems, but the histogram has an X and Y axis that you'll use, and that helps to develop this visualization. All right, so that 68, 95, 99.7 rule, that's known as the empirical rule. Again, about 68% of the data falls within 1 standard deviation. The 95% is 2 standard deviations. The 99.7% is within 3 standard deviations. Now, what happens if we're outside of that 3% or that 3 standard deviations? Those are called outliers. And there's a general rule of thumb that outliers are at that 3 standard deviations, although there's an argument that maybe that's not accurate. It really depends on your data. And statistically, you have to know what your data is about, where you got it, and use your oftentimes just a human instinct to know, does it make sense to have these outliers or not? Sometimes if you're using survey data and you can use this rule to figure out if maybe somebody just answered all of the questions on the survey with the same answer, that's probably an outlier and you could remove them. If you think that those answers are still true or could possibly be true, then you'd want to include them even though they may look like an outlier. The debate between should it be 3 standard deviations or 1.5 standard deviations has raised some question about, do we remove outliers at all? And so that's not for this class to debate, but we just so that you know, moving forward, if someone says, well, do you have outliers in your data? It's not an easy answer. Maybe you do, maybe you don't, but it's a decision you have to make as the researcher, whether or not you'll remove those. All right, so here's the mathematical representation for normal distribution. We're not using that in the class. You don't have to do this longhand on paper, but it just lets you see what that would look like. We have talked about measures of central tendency, again, mean, median, and mode, but I want to talk more about normal distribution and the importance of that in statistics. So we're going to now talk about central limit theorem, statistical inference, and modeling real world phenomena. Okay, so imagine you have a big jar of candy and you've probably seen these guessing games before. You want to know the average number of chocolate candies in different handfuls that you would pick from the jar. So this is a fun exercise if you've done this before. Typically people have all different ways of how to do it. They just guess, or they go through and meticulously count a certain color or a certain square within the jar, and then they multiply it by something. So seems like everybody has their own way of doing this, but no matter which way you do this, there's a big picture, there's a pattern, and then there's this why it matters. So no matter what the distribution of candy types are in the jar, there's a lot of chocolate, there's a few chocolate, and sometimes there's a random mix. If you keep picking the handfuls of candies and calculate the average, those averages will start to form a pattern. If you make enough handfuls, the pattern of these averages will start to look like a bell-shaped curve or your normal distribution, assuming this was truly a random sample of candy in the jar. This is true even if the original mix of candies wasn't distributed evenly with a bell-shaped curve. That's true to some extent. Sometimes people hack this and they only have a certain number in there. But if it's truly random, and we can just dump it right out of the bag, this should work. So this means that no matter what the original distribution of candies was, if you take enough samples and calculate their average, those averages should follow a normal distribution. That helps with predicting and understanding your data better. All right, so when scientists or analysts study data, they assume their data follows a normal distribution. This is something that we can't truly assume. You can assume it at the beginning, but you have to test it at the end to make sure that the data is normally distributed. If it's not, then we have other tests that we can run that looks at the data if it's not normally distributed. In this case, we're just using the z-score, so that helps us to see how many standard deviations from the mean that we have. Many statistical methods work best when the data follows this bell-shaped curve. For example, if you're comparing test scores from two different schools, you might assume that those schools are normally, or scores are normally distributed. What I have noticed is if you're using test scores from different schools, but they use it on a different scale, maybe they're using a 4-point scale or a 5-point scale, that's where it gets more complicated, and using a z-score would be helpful. So why it helps. The assumption allows them to use powerful tools and techniques to make predictions or conclusions from the data. For example, they can estimate how confident they are in their results or test if differences are significant. And then finally, with the real world phenomena, you can use this with just about any industry, any type of data whatsoever. Finance, biology, engineering, real world data often tends to fit the normal distribution pattern. And regardless, it's something that you should test, because again, if it's not normally distributed, there are different tests to use, and we wouldn't want to use the same test across the board. Last week, we looked at correlation tests. We used the Pearson correlation. If that was normally distributed, Pearson's fine. If it's not normally distributed, we'd want to use the Spearman test. So there's, again, different tests to use depending if your data is normally distributed or not. Okay, and then as we conclude, the empirical rule states that in a normal distribution, approximately 68% of the data falls within one standard deviation, 95% within two, and 99.7% within three.